Oceanit to help train future leaders in the technology, science, and engineering business for the future. Here's people that have done things that are out of the ordinary, and very few people represent that like Earl Bakken does. He's a really interesting guy. I mean, as I've gotten to know him, and it's like talking to somebody, you know, you might meet at the hardware store. Very easy to talk to, real down to earth, but a visionary like very few people that you're going to meet. You'll hear a little about it. The forum that we try to follow is we ask people to talk a little bit about themselves, a little bit about some of the things they've done that are very unusual or different. What do they see in the future? And then we try to have a little bit of time for questions and answers. And Earl founded a company called Medtronic, which is a huge company today. I think it was like 1949. And today it employs about 25,000 people?
30,000.
30,000 people. It does a gross, this year it'll do about $9 billion. Pretty close. And the thing that's really fascinating about it, besides the fact that it's such a large company and an influential company, but there's a genesis that occurred. It's sort of, if you follow this tree, you'll find that there's one of the key roots in this creating a medical industry that's really part of the northeastern United States today, is this man. And the jobs that have been created and what it's done to their families and how it's changed the community is profound. And it's really important to understand that, because in Hawaii today we're looking to the future and we're trying to see, you know, what does the future hold and what are some of the possibilities. And I think Earl is really a great example of how an individual and a company, some great ideas and some hard work, can change things in the community in a way that's beyond imagination. So anyway, before I go on saying any more, I'd like to introduce Earl Bakken.
I'm enthused about Patrick and what he's doing here and what he can do here in Hawaii, and his dedication to doing it in Hawaii is very exciting. To me, I'd like to see more of that growing on all over, and I'd like to see it happen on the Big Island. We have a few electrical engineers there, but we need a lot more ones with Patrick's drive and enthusiasm for getting things done. So it's a pleasure for me to come and talk to you and see what's happening in your medical division, Juana. And it's very fascinating work. Okay, I was born in 1924, so I'm getting along in years. And in a few months, on the Big Island, we're going to be celebrating my 80th birthday. When I was about 4 years old or 5 years old, I began my career in electrical engineering. But in those days, in the mid-20s, electricity in homes was on porcelain insulators and wires across the ceiling, and then a light bulb and a pull chain to turn on the light bulb for the light. But electricity was very open. You could play with it very easily. And I got fascinated by playing around with electrical things that were available back then, which weren't many. So either 8 or 9, I first saw the Frankenstein film, the original Frankenstein. Has anyone here seen Frankenstein? You're all so young. This picture, to me, was a very inspirational picture. Here in Dr. Frankenstein, the film came out in 1931, and I'm not sure when I saw it, in 32 or 33. But Dr. Frankenstein used electricity for reanimating this creature that he had put together from stolen body parts that they had robbed from the graveyards. And I was quite thrilled by that idea of bringing life back into a body that was dead. And it gave me the idea of doing something like that when I grew up. I said, this is what I want to work with, is something that uses electricity in the human life, Boucher and Aldini and others, in stimulating bodies that had been executed by the guillotine. So the guillotine really was the start of, I think, of Medtronic. Because when they got these bodies with the head cut off, the bodies were still oxygenated for up to 3/4 of an hour. They could stimulate the heart with a Leyden jar, with a charged capstan. And they would put heads together and yell at the heads to blink their eye if they heard them and things like that. But there was a great deal that was learned about electrical stimulus of parts of the human body because of the guillotine. My wife was working in a hospital, and they knew being I was in electrical engineering. When I'd stop by there in the evening, they would ask me to try to fix some of their equipment, colorimeters and flame photometers and EKG machines, and I would do that. And so one evening at a birthday party, I was together with my brother-in-law, and we said, maybe there's a business in servicing, putting up a service quality service in medical electronics. So we started with that. And the first month we were in business, we had one service call on a centrifuge. And so we grossed $8. And that was really the beginning of Medtronic. Now there are babies born with a hole in the heart right where the conduction system there is shown together, right there at the top of the ventricles. There can be a hole in the heart. So the blood flows from the right side of the heart to the left side of the heart and vice versa. And then the blood that is then pumped around the body is not oxygenated as it should be, because a lot of it has mist going through the lungs and is just gone from the right atrium to the left atrium, and the babies then have a bluish tint, and particularly when they run, they get kind of blue colored and they stoop down because they get very tired. And these kids were all dying in their early years or when they were teenagers. And Dr. Lillehei's thought was to go into this right ventricle, the one on the left of the scene here, stop the heart, go into the right ventricle and sew a plastic patch over that hole in the septum between the two ventricles. And to do that, he'd have to stop the baby's heart, and there were no oxygenators. So what he would do is use a parent who had the same blood type, and cross-circulate the blood through the parent. Can you imagine that today? Yet, when I mention this to doctors today, they just can't visualize that using a parent as the pump oxygenator. But they had to use a parent as the oxygenator to flow the blood through a parent to keep the baby's brain alive during this stopping the heart. So they would stop the heart, go in and sew a patch over the hole, and then start the blood circulating again and disconnect it from the parent. And the baby would have a fine mechanical repair. But when they were in there sewing that patch over that hole, they would traumatize the conduction system there, shown in blue. And the baby would end up with a slow heart rate. And most of these babies would die within a few days post-surgery. So Lillehei came to us and said, there's some way you can help us keep these hearts beating post-surgically. So we tried connecting the heart directly, and this machine puts out 150 volts, and all we needed was 2 or 3 volts to stimulate the heart directly. But that was quite a happening. to put a wire into the human heart and stimulate the heart directly. And then the wire was brought out through the chest when the chest was cold, and we connected the machine directly. Dr. Lillehei came to me and said, isn't there some way we could keep these pacemakers beating during a power failure? And so what I looked for was an electronic metronome in a box that put clicks on a loudspeaker, just like the mechanical metronome puts out clicks. And it was a 2-transistor circuit, a blocking oscillator and a switch, one transistor acting as a switch. And that blocking oscillator had the frequency that I wanted to use in a pacemaker that would substitute for this big machine. And so I plagiarized that circuit and put it in a box, and it looked like this. This is not it, but we put it in a box like this with 2 transistors and put a output control and a rate control on there. And this then I brought back to the university one day, and we tried it on dogs, and it had a small battery in there that produced about 9.4 volts, and we could get that output out of the unit. We tried it on a dog, and it worked because it put out the same signal as the big machine cut way down. And I came back to the University of Minnesota the next day, and I saw this pacemaker attached to a child's chest. And I can tell you that was a multi-emotional moment, because I said, you know, this is quite a thrill to see something we have made with our own hand, keeping a child alive. And yet have we made it a quality to actually be used to keep them alive? Because if it quit, the child would quit. Anyway, this used to be a black crackle finish, but they used this pacemaker on so many children and put tape over it. They had to put tape over it because the kids would start playing with the knob. And that isn't too good. Changing rate or to be shutting it off. And if they didn't, their playmates in the heart hospital would. I like the idea of when you're providing a device, I believe in ready, fire, aim. In other words, carry out the idea if it's a reasonable idea, and then figure out where the problems are and readjust your aim. So that's what we did. We made the first pacemaker in 4 weeks from the time Dr. Lillehei and I talked about it till we were trying it on dogs, and we used on humans in 4 weeks. Today you couldn't do it in 4 years. But we were saving lives within 4 weeks. But the mission is so important to have a mission-oriented organization, and that everyone understands their job is to complete that mission. And I have everyone in our company believing their task is to help the patient, to see patients